Okay guys, welcome to my YouTube channel. Today I'm going to talk about significant figures and actually numbers and measuring. So measurements and numbers, before we start doing significant figures and scientific notation, numbers and all those, I want to introduce the perception of accuracy and precision. Okay, precision means if you're doing a measurement and you're doing points, you're getting data points that are close to one another. So in terms of precision, both of these you could see are precise because the dots or the shots that you have done are pretty close to one another, and you have a less precise and also less precise targeting or aiming here. As you could see, shots are actually very sparsely packed on the target, as you could see. Now, if you aim the target and you do a very good job and you're measuring something and you're doing very close to the accurate measurement, the real thing, the real true amount that you're measuring, and if you're doing actually, if you're playing dart, meaning that you could hit the center or you could do a best shot, you could actually target at the very center of your target. Actually aim at the very center of your target. If you do that, it means you're being accurate. So in terms of accuracy, this one is very accurate. This one is also accurate. It's not just precise. Okay, so in terms of the one that is both precise and accurate, this one is both precise and accurate, densely packed and also close to the center. Densely packed but not close to the center, so it's not accurate but it's precise. This one is not precise, widely spread, but around the center, so it's accurate but not precise. This one is neither precise nor accurate. It's not densely packed and it's also not close, not aiming at the very center. So that's what accuracy and precision means. Let's move on. So this is a good analogy in doing if you're playing dart, but let's just move into the target. Let's say we have a beaker like this, or an Erlenmeyer like this. These are called beakers. Erlenmeyer like this that measures 25 milliliters. Okay, let's do that. And if we fill this 25 milliliters with an Erlenmeyer and then try to actually pour it onto a graduated cylinder and see how much it is. Okay, let's say one student did that 5 times and find out that it's when measured the same amount, the same 25 milliliters that the Erlenmeyer says, it's 20, 21, 24, 28, 30. Another student did the same thing, and in another group, let's imagine that we did it in a lab situation, 15, 16, 19, 23, 25. So you could see this one has done another very good job on this. Another one has done the same thing and find 23.3, 23.1, 23.4, 22.6, and 22.5. You see that it's good measurements, but they are far less, they are not very close to the 25. And then let's say one of our best friends, like one of our smartest students, did 24.3, 24.9, 25.1, 25.2, and 25.5. Okay, let's say we have these kind of measurements and we want to see the same exact effect that we have here. Which one is accurate, which one is precise, which one is both accurate and precise, and which one is neither accurate nor precise. To measure the accuracy, we kind of see the standard deviation from the center. Okay, the average, and how average is far from the real amount, which is the 25. Okay, so let's do the average in all of them. And this one, the average, if you do it, add them all up and then divide it by 5, you will find x bar for, or the average, we called it x bar in mathematical language, that is going to be 24.60. For this one, the average, you'll find x bar is 19.6 for this one, so not accurate. for this one, the x bar, you find x bar of 3.88. My bad. Sorry. X bar is 22.98, so not accurate again. And the last one, X bar, is just 25.0 or 0.00. So you could see that this one is accurate. This one is also accurate. Okay, let's just use the same color to denote the accuracy. This one, the one that are accurate have the average that is close to 20, more closer to 25. This one and this one are less accurate or not accurate. Okay, let's now do the standard deviation. And a standard deviation, I write down the formula once, and then we will use the same formula for all the three. Okay, and accurate, let's just put accurate here on the top, or here you could see it, it's accurate, the first one. A standard deviation, it's x bar minus xi to the power of 2, the difference to the power of 2, and the sum of all those, like the sum of all those 5. That gives you the standard deviation. And if you do the standard deviation for all, and you call it sigma, like that is the symbol for it, sigma, that's the Latin word. And the sigma, the smaller the sigma, the more precise the measurement. If you do sigma for this one, you find a sigma of 3.88. So not very accurate, maybe. Not very precise, my bad, maybe. This one, if you do sigma for this one, you would also find a sigma that is 3.88. So this one is also not that precise. And you could find the other one with a sigma that is 0.37. Sigma is 0.37, so it's very precise. And the last one gives you also a sigma of 0.40, so it's also very precise. So the last one is both accurate and precise. This one is precise but not accurate, so this one is not accurate but precise. This one, we find that it was neither accurate nor precise. So no accurate, not precise. And that last one was not precise, but it was accurate. Okay, so that's this. Now let's move on to another topic. I want to speak now about the idea of the number of significant figures. How does that work? Let's just move on to that thing. For the number of significant figures, we look on the numbers. Let's just do a bunch of numbers and I'll discuss, and I have my selection choice of those numbers is that, so you have every kind of example. Okay, so 14.3, 7300 with the dot at the very end, 0.0012, 23.00, 1200, and 1.7 times 10 to the 23. Okay, now all the first 5 number are numerical notations, means it's numbers. We have also one number that is in scientific notation. It has a coefficient and it has a power side to it. So it's two segments, power segment and coefficients or a numerical segment. Okay, we will talk about the scientific notation in depth in this video, but first let's talk about this the significant figures. I want to write them down in different colors using the using the another color to actually demonstrate. Okay, so I use blue here, and you could see that now we have three. If I do color them, it means it's significant figures, three of them. How do I know that? Any number, my bad, that is a digit, we're going to count it as a significant figures. How do I know whether I count the zeros that are preceding or not? Well, if it's after a big number like this, you don't know until you have a decimal point. If you have a decimal point, it means somebody has measured them, so you count them in. Okay, so I count this one and I count this one just because of the zeros, and it gives me 4 significant figures. Now let's move to this example. I do this. Now here I don't have a decimal place here, so I know that those two are not among those. So only 2 significant here, while there are 4 significant here. So the decimal is important if it's after, if there's some zeros, because zeros sometimes don't count, sometimes they count, we count them. If they are preceding a number, like before a number, you don't count them, never. But you count them if they're in front of a big number and there is a decimal place after them. So 4 here, but not decimal place after a big number, we don't count them. So just 2. Here, zeros that are preceding, I never count them. So 2 significant figures here. And also for this one, if you literally have a decimal place and after it, like after a decimal place, you're adding some zeros, it means you have measured them. Like this one is 4. Let me just give you another example. If I have a 0 here, because I have a decimal place and I'm adding this, there's no means for me to put another decimal place here. If I just put the 0, it means that 0 is counted in. So I then would have to count that 0 as well, and it gives me 3 significant figures. And also for the standard notation, you just look at the part that is the numerical part, and I just have no zeros in it, so I count all the 2 numbers and it gives me 2 significant figures. Okay, and one more important thing is that if you write a number in this notation or in this scientific notation, it won't change the number of significant figures. Okay, now let's go to the conversion between the 2 types, between the numerical notation and the scientific notation. How do we do that? How do we convert? Okay, so when we want to convert, it's just to decide whether the number is big or small. And in chemistry, always we're interested in the numbers that are small. Okay, and it's also a matter of how many zeros are at, and then we're going to count it. So let's just talk about a number that we want to actually write down. So let's talk about this one. And also this one. For the scientific notation, this is the numerical notation, a very small number, a very big number. For the scientific notation, there is a standard form that we used 1 digit. Okay, so if I use this 1 digit, it means it has to start from here all the way to all those numbers. So I'm going to actually have them in different colors. Okay, so I don't count the zeros that are preceding. And for this, if I want to express this number, I have to actually count all this. But the only one that I colorize is this one. Okay? So here, I'm going to say this one, the first digit, that is this one, I'm going to say 1.73 times 10. Then I count back to here, to this place. So 1, 2, 3, 4, and it's getting smaller, so minus, because it's getting smaller than 0, 4. And again, that 4 means the first digit of that number, and you count back from there. And that's why do I count from here? Because I just put the decimal place intentionally here to make it one digit, to make 1.73. Also, I do 1.73 here times 10. Let's do a -4 in different color so that's visible. And I now count from the where I start, from the decimal. On the top, I count to the decimal point on the small number. On the big number, I count from the decimal point all the way to my number. Okay, so that's how I do it. 1, 2, 3, 4, 5, 6. So it's to the power of 6. This is how you make a scientific notation, a numerical to a scientific notation. If you have that and you want to write that down, the way you have to do it is you put a number of zeros and then you locate your first digits. Let's just do that real quick. Let's just say 4.12 times to the 10 to the -4 and 0.12 times 10 to the 5. Okay, if you want to write down these two numbers in numerical form. So I just count down. This is a very small number, so that's my decimal place, and I have to count down until -4, until the fourth place, and then I start by 4 because that's the first number after the decimal. So 1, 2, 3. Let me just get more space. 1, 2, 3, 4, and that's my 412. And these are zeros that I need to put now. Okay, so first, second, third, and fourth place after the decimal, because that's a small number. This is the big number, and I'm going to move that decimal 5 place to make it bigger. So 1, 2, 3, 4, 5. It means it has to be a 12, and then 2 zeros following it to make 4 to 5. Okay, that's also the exact same thing. You could move the decimal place 4 times to get that number. Let's see, what do we get? 1, 2, 3, 4. It means it has 1, 2, 3 zeros. That's what also we wrote there. Okay, so you just move the decimal place to the position that you want. That's how you do this. Now, what is good about doing scientific notation? What is beneficial about using it? Atoms are very small. Actually, things are very small in chemistry. We will talk about dimensions, but just to give you a sense, I have a presentation of a bacteria, E. coli here. This is in the order of micrometer. That is micrometer, 10 to the -6 meters. So you see how small it is. And I have a presentation of a Buckminster molecule here, and that is in the order of angstroms. Okay, I believe some 25 or 20 angstroms in diameter. So that's, each angstrom is 10 to the -10 meters. So it's way smaller than the bacteria that I just showed on the top, the E. coli bacteria. Okay, so that's how small the molecules are, and why do we need those small molecules, those small numbers. Atoms and molecules are very, very, very small, so we need to know the scientific notation. So I just showed you how to convert between the numerical and the scientific, and from numerical back to scientific notation. I want to just go on and present how you could actually change and play with the scientific notation. Let's just focus on 3.12 times 10 to the -7. Now this, I told you, this is the standard notation. I want to talk about what happens if I want this as a bigger number, like if I need it as 312. Now, how can I do that? What the most important thing about scientific notation is that you could change this coefficient to a smaller or bigger number. But if you did that, you have to actually compensate in the power side. So you could do this, but then you have to change this. Now, how do I have to change this? Now, this number is bigger than 3, like 300 is 2 orders bigger than this. So I have to make this one 2 orders smaller. And a smaller means more negative, so 10 to the -9. Now, can I make this bigger? Yes, certainly you could. Then, if I have 0.0312 and I need this, can I write that in that form? Yes, the standard notation is just one digit, but if I need this, I could do that. Now I have made this one 1, 2, 3 times smaller, so 10 to the, this one I have to make it bigger, so less negative 3 times minus 4. And minus 7, make it 3 times bigger, is less negative 3 times, and that's a minus 4 here. Okay, if it's positive, it's easier, but I just did the negative one that is a little bit more challenging, okay, so that you kind of know both situations. If it's a big number, that's certainly easy to make it bigger or small. I just do one small thing. Let's just do 3.12 times 10 to the 23, and I want this. Now 10 to the what, if I made this part smaller by 1, 2, 3 times, I have to make this one bigger 3 times. It means adding 3 to this, so 26. And that is if I needed this number, okay? And I want to wrap up the video by giving examples of how do we actually add up, how do we multiply, and how do we actually divide these numbers in scientific notations, okay? I do 4 examples, and I want to show you real quick first the division and multiplication, and then the adding and subtracting, okay? Let's do 1.73 times 10 to the minus 4. If I want to multiply it by 5 times 10 to the negative 6. And if I want to divide that same two numbers, like this divided by 5 times 10 to the negative 6. For the coefficients part, I just do the math on my calculator. This times 5. And that gives me, if you do that, you will find 8.65. Let me just do it. I just put it on the top because I need more space here. 5, 6 times 10 to the. Now these two, we just add them up. Minus 4 and a minus 6 is a minus 10. So the powers in the power series, we just add them up and then multiply. We just multiply these two numbers. If I divide this, it will give me 0.346. Now that is in the standard notation. The first time you learn this, you don't need to care about the standard notation. As you go on, you need to actually fix yourself for the standard notation, because I showed you how you manipulate. You could make this bigger or smaller the way you want if you play with the power part, just like we did previous example. Okay, so if I divide this, and then it would be minus 4. If I do divide, it means minus, because it's plus here. I do minus 4 plus minus 6, which is minus 4 minus 6, which gives me minus 10. Here it's minus 4 minus minus 6. Minus minus is just plus. So minus 4 plus 6 is just 10 to the 2. Okay, and 10 to the 2, you could just write it as the standard notation, 3.46, make it bigger, and you have to make this one smaller, so 10 to the 1. And 10 to the 1 is not, nobody uses that, like this times to the 10 as a scientific notation, so you just do 34.6. Okay, that's your number. And like it's an easy number, we don't have to do a 34.6 in the scientific notation because it looks a little bit awkward. Scientific notation is very useful if you're doing a small number or a big number. So that's the answer for multiplying and actually subtracting. Let's go on and add them up, see what do we have to do for adding or subtracting. Now there is one small thing that I want to mention before I talk about that. And if you want to add 300 or 3000, let's do, with 0.05, the first thing you do, you put the decimal place by one another. Okay, so 3000 and, oh my bad, 500. So it would be 3,500. Okay, so just put the decimal places by one another. For the scientific notation, numbers notation, we have to make sure, we have to do this. That's the part that we actually need to do. But we need to make sure that the power part of both numbers are at the same order so that we could add them up or multiply, or my bad, not subtract them. So for addition or subtraction, you have to make sure that the power series are in the same order. So if they're not, you have to make it just like we showed on the previous example. So let's say what we do if we have 1.73 times 10 to the minus 4 plus 5 times 10 to the negative 6. I'm going to do this in two ways. The first, I'm going to actually make the first, and you don't need to do that. I'm just going to show you that it's possible in two ways. The powers here, the tens power, are not equal, so I'm going to make this one equal to minus 6 or make this one equal to minus 4. Let's first do the first one. It would, if I change this to a 10 to the minus 4, it means I have made this one bigger, so I have to make this one 2 times smaller, like say 0.05. Okay, that's what I need to do, times 10 to the minus 4. Now that's the same number. I can add the 2 up, or I could do this one to the minus 6. So it's first way. The second way is to actually do the same exact number, and this one, I'm going to make it to the 10 to the minus 6. If I make it to the 10 to the minus 6, it means I've literally shrunken or decreased these 10 to the minus 4 here to the 10 to the minus 6, which is 2 orders smaller. So I have to just make this one 2 orders bigger. So 173, okay, times this. Now that's the same number. I can add it up with this because they have the same power. So I'm going to add these two or these two, and they'll both give me the same number. Okay, I would have either, if I add these two, you have 1.78 times 10 to the negative 4, or if I add these two up, you would have 178 times 10 to the negative 6. They are the same number. Like you could change this one to the 10 to the minus 4. You have to make it 2 times. You have made this 2 times bigger, so you have to make this one 2 times smaller, and if you do so, you get the same number. Or you could change this one to this, and you could see that these are the same exact numbers. Okay, if I want to subtract them, that's the exact same story. On the top you will find, like with this one, if I do now subtract, and with this one, if I do subtract, okay, if I do so, I will get, let's see, 1.68 times 10 to the minus 4 for the subtraction, and for the subtraction down below, here we get again 168 times 10 to the minus 6. And those are also the same exact numbers, just with the same rationale we used there on the top. Okay, I don't know, it always goes lengthier than I wish, but that's it for today, and we will wrap it up here, and we will actually follow next topic in the next video.